Okay, so this is a section that you should have learned about in Chem 1A. It's here in Chapter 20, but it's in the course outline of record for Chem 1A, and so I know in my class I taught it. So these are those same exact slides, but I think you could use a refresher. So oxidation and reduction, right? And reactions that involve oxidation and reduction are often called redox reactions because it's fewer syllables, easier to say. So there's a couple of ways to remember what oxidation is versus reduction, because as with so many things in science, there's a lot of pairs of things, and it's easy to get them crossed, right? So this is one that I learned, oil rig. So oxidation is loss of electrons. Reduction is gain of electrons. So if you're looking at a substance and it's gaining electrons, reduction is gain, that substance is being reduced. I think this is more where the term came from, really. We talk about oxidation states, we'll review those in a minute, but oxidation is an increase in the oxidation state, and reduction is a reduction or a decrease in the oxidation state. So in any redox reaction, you have to have both of them happening, because one's losing electrons and those electrons have to go somewhere. And the thing gaining electrons has to get them somewhere. There's no homeless shelter for electrons where you can go, and pick up some extra electrons or drop off the ones you don't need. They all have to be accounted for. So in a redox reaction, we have to have the mass balance, which is, what we're all pretty familiar with doing in terms of balancing a chemical equation. But we also need to have the charge balance. And a lot of these reactions, because of the numbers of electrons being transferred that are not obvious in looking at the reactants and products, they're pretty much impossible to balance by inspection. And so we use the half reaction method, where we take the reaction, we break it into two half reactions, one for the oxidation, one for the reduction. We balance them separately, and then we put them back together. Does that sound familiar? So reviewing oxidation states, also from 1A. And as with lots of things like playing a board game, if you read the instructions, it sounds super confusing and hard, right? And you're like, I don't want to play that, doesn't sound fun. But if you're watching some other people playing, and they're like, no, come on, it's fun, and then they'll just kind of correct you, and after a while you see, well, it all makes sense now. That's the way this is. So, the written out rules are really more confusing than the process actually is. So basically, and I can say basically because we're not in the acid-base chapter anymore. Oxidation states are a man-made thing. They are different than ionic charges. But the oxidation state is often the same as the ionic charge, which makes it both confusing and easy, right? So free elements like sodium atom, what's the charge on a sodium atom? Atom, not an ion. 0, right? All atoms have 0 charge, right? So they have an oxidation state of 0. So any element, chlorine, Cl2, does it have an overall charge? Nope. Oxidation state is 0. Monatomic ions have an oxidation state equal to their charge. So the sodium ion, +1. The ion is +1. Its oxidation state is +1. The sum of the oxidation states of all the atoms in a compound is 0. Just like in a compound, the sum of all the ionic charges in an ionic compound have to be 0 because the compound is neutral. So if we know one of the oxidation states and not the other, we know they have to add up to 0 because it's neutral, and so we can figure out what the other one is. So a neutral molecule adds up to 0. In a polyatomic ion, the sum of the oxidation states adds up to the charge on the ion, right? So here we have the example of nitrate ion. It has a -1 charge overall. So the oxidation states of the nitrogen and the 3 oxygen atoms that are bonded together within the nitrate ion, the oxidation states add up to the charge. Again, it's acting like ionic charges. Metals always have positive oxidation states, just like they always have positive charges. So this part's kind of redundant. Group 1 has a +1 oxidation state. Well, of course it does. They have +1 charges, right? Group 2 is +2. Just kind of saying it over and over again. So this is the part that is different, and we need to remember. So what about the nonmetals? Like if you're looking at a molecular compound composed of nonmetals, overall the charge is 0. How do you figure out what the oxidation states of the nonmetals are? Well, you use these rules. So you're going to go through the compound, and if you have fluorine, it's going to have an oxidation state of -1. What charge does a fluorine ion have? -1. If you have hydrogen, it will have a charge of an oxidation state of +1, which is the same as a hydrogen ion charge, right? Oxygen, its oxidation state would be the same as the charge that an oxide ion has. Group 7A elements form -1 ions. They will have -1 oxidation states. Group 6, -2. Group 5, -3. So the way I think of this is it's like a list of who gets first pick, right? And we don't need to understand why or how this works. That's not really that interesting. We just need to remember this. So fluorine, if it's there, always gets first pick. And they're going to pick the oxidation state that is the same as the charge they would have if they were an ion. Does that make sense? And so once you get through these guys, whoever's left at the end has to take up the slack and make up for what everybody else got. So how do you remember this? Oops. Remember, I have a Band-Aid, a Band-Aid on my thumb, and so it doesn't work on the tablet. So you know what pho is, right? Really yummy noodles. So, there. It's an F. It's the F sound, right? So pho 765, and I think there's actually a restaurant called Pho 76. They just need to add a 5 on here. So we can remember that. Pho 765. Fluorine, hydrogen, oxygen, 765. That's the order. You don't need to remember the oxidation states because you already learned the charges, and they're the same. Any questions? Pho 765.
There's a Pho 76 and 75.
Cool.
And they're like down the street from each other.
That's awesome. I should go there, take a picture of their sign at least. Okay, so here's the procedure for the half reaction method. This is for balancing aqueous redox reactions. And again, set of rules, kind of confusing. The first step, assign oxidation states to all atoms and identify the substances being oxidized and reduced. In my opinion, we definitely need to be able to know how to do that, but you don't actually have to do that to balance the redox reaction. So that one's actually kind of optional. But you definitely need to do everything else. Separate the overall reaction into 2 half reactions. One will be oxidation, one will be reduction. We're going to balance each half reaction by mass for the atoms in this order. Balance everything but hydrogen and oxygen. Then you balance oxygen by adding water molecules as needed. You balance hydrogen by adding H+ ions. And we're not throwing new reactants or products into this thing because this is happening in aqueous solution. There is water all over the place. So it's fine if water is going to participate in the reaction. Are there hydrogen ions present in pure water? Yup. At a concentration of 1 times 10 to the minus 7 molar, right? So this is an acidic solution. Are there hydrogen ions present? Absolutely. So one of the things with balancing these redox reactions is might have one side that has oxygen and the other side has no oxygen in the products. And you're like, well, how does that work? Well, we have to take these species from oxygen to balance it. So we balance for mass, and then we balance with respect to charge. And we do this by adding electrons. Because 1/2 reaction is oxidation and 1 is reduction, one equation will have electrons as a reactant and 1 will have electrons as a product. If that doesn't happen, you did something wrong. You should start again. We need the sum of charges on each side to be equal to each other. The sides just need to balance. They do not both have to be 0, okay? They just need to be equal. So now we've got 2 half reactions that are balanced with respect to mass and charge. We want to add them together, but we don't want any electrons to show up in the final equation. So we're going to do this step. We're going to make the number of electrons in both half reactions equal. So if one has 2 electrons and the other has 1 electron, we'll multiply the smaller one, all the coefficients, by 2. It's still balanced. But now we have the correct number of electrons so that when we add them together, the electrons will cancel out. Sometimes other things will cancel out as well. And then the last step is always verify that the reaction is balanced. So let's do an example. And so this is little, shorthand here to remind us what are we supposed to do. So we can assign oxidation states. Let's do that just for practice because it might have been a while. So what's the oxidation state on a hydrogen ion? +1. How about this chromium? 0, it's an element. How about this one? 0. How about this guy? +2. So that wasn't much of a challenge. But we can see that hydrogen is going from +1 to 0. Chromium is going from 0 to +2. So one's going up in oxidation state, the other is being reduced, a reduction in its oxidation state. Which order you put them in here really doesn't matter. It'll all work out in the end. It's helpful to make sure that your arrows line up. So I like to start with the first one. So we're going to put H plus aqueous on that side. And then it's usually pretty obvious which of these belongs with that one, right? We can't turn hydrogen ions into chromium ions, right? But we could turn them into hydrogen molecules. So those two go together, and then the chromium and the chromium ions go together. Two half reactions. Now we need to balance them, and sometimes this is really simple, and other times it's not so simple. Is this first half reaction balanced with respect to mass? No. How can we fix that? We'll put a 2 in front of the H plus, right? So we have 2 hydrogens and 2 hydrogens on each side. Down here, is this balanced for mass? Yes, it is. Okay, so we're done with that. We didn't have to mess around with water or adding hydrogen or anything. Now we're going to balance with respect to charge. So on the left side, I have 2 hydrogen ions. It's a total of +2 charge. On the right side, I have 0. I need to make them the same by putting in electrons. So I add the electrons to the more positive side. So 2 electrons plus 2 positive ions will give us a total of 0 charge on the left. We have 0 charge on the right. It's all good. How many electrons do we need for the second half reaction? 2. And are they going to go on the right or the left? On the right, because we have +2 charge over here. So make the number of electrons equal. Cool, we already did that. Add them together. So the 2 electrons here cancel the 2 electrons over there. Because what's happening is the 2 electrons produced by this half reaction are consumed by that half reaction. That's why they don't show up in the final equation. Nothing else cancels out, so we'll just copy it down. And then we should always verify. So 2 hydrogens, 1 chromium and 1 chromium. Total of +2 charge over here, total of +2 charge over there, it's balanced. Any questions? Yes?
In terms of figuring out whether a reaction is a redox reaction or not by what's given to us, can we assume that it's a redox reaction if there are hydrogens or oxygens missing on one side of the reaction?
I would say yes. If you're given an unbalanced chemical reaction and you're missing hydrogens or oxygens from one side, how can I balance this? There's no oxygen to put a coefficient in front of. It's almost certainly a redox reaction. Yeah. Any other questions? This might have been helpful before you had to balance that equation in experiment 26. Okay, so you know what's really, really funny about that equation? That's the same one you used in your lab practical in Chem 1A. You could have looked in your Chem 1A notebook, and it was just there. But I didn't tell you that because you guys were learning about balancing, right? It's good for your brains. Okay, let's see. How many of these do I have here? Which one do you want to do? Iron and permanganate or copper and nitrate? Let's do one. Nitrate? Okay, we'll do this one. I don't think we need to do both of them. So this one doesn't have the steps on the side. But the first thing we have to do is separate it into 2 half reactions. So, yeah. Come on, cooperate, silly thing. So we've got copper, and we've got nitrate ion. And the copper, of course, is going to turn into copper ion. And the nitrate ion is going to turn into nitrogen dioxide gas. What's the next step? Balance for mass. Is the first one good? First one's good. 1 copper on each side. It's not balanced for charge, but we're not worried about that yet. Down here, the nitrogens are balanced, but this one has 3 oxygens and that one has 2. You can work on that all day long, putting coefficients, and it's never going to work out. Right? It's never going to work out because you fix one, you mess up the other. So we need to add water molecules to balance the hydrogen. So this side has balance the oxygen, sorry. This side has 3 oxygens, that side has 2. We need another oxygen over here, and we're going to fix that by adding a water molecule. We're not going to add oxygen. This is in an aqueous solution, an acidic aqueous solution. We can only add things that are definitely present there. So that's great. We fixed the oxygens now. We created a problem with hydrogen, right? There wasn't hydrogen before, and now there is. We have 2 hydrogens here, but we can fix that by adding hydrogen ions. And the reason you want to do those last is because they don't mess anything else up. What do we do next? Charges. So we need some electrons. How many and where do I put them on the first one? 2 on the right side. Is that oxidation or reduction? Oxidation is loss of electrons. Or you can look at, this went from 0 to +2. So that gives me a clue. I'm going to need the electrons on the other side down here. This side is easy. It adds up to 0. Here, you need to be a little bit careful. And you feel dumb using your calculator, but it's even worse to do this whole problem and get it wrong because you added negative numbers wrong. So it's okay to check this with your calculator. I have a +2 charge here and a -1, so overall that's +1, right? So I need 1 electron. So a negative and a negative and 2 positives give me 0. Now what do? We need to multiply the second equation by 2 because we have 2 electrons here and 2 there. That was stretching, right?
Yeah.
Okay, just checking. So I'm going to multiply every coefficient by 2. That maintains the balanced equation. So this becomes 2 electrons. This is multiplied by 2, it becomes 4. This is 2 and 2 and 2. Still balanced. Now we can add these together, and the electrons are the same on each side, so they cancel out. And we just copy down. Remember, it's like adding. 1 + 2 is the same as 2 + 1. It doesn't matter what order you put these in. So, and actually mastering chemistry doesn't even care. So then you know it's really true. So copper plus 4 hydrogens plus 2 nitrate ions is going to give us copper ion plus 2 nitrogen dioxide molecules and 2 water molecules. Then always you should check. Any questions? So that's an acidic solution. What about basic solution? Well, in a basic solution, we do not have a lot of hydrogen ions present, right? We have more hydroxide ions present. So the process here is we're going to go through the same steps. We just need to do one thing differently. After we balance for mass and charge, we want to neutralize the hydrogen ions by adding an equal number of hydroxide ions to each side. So if I have 2 hydrogen ions on this side of my equation, and it's all balanced, there's other stuff there, I can add 2 hydroxide ions to both sides without messing up how it's balanced. And 2 hydroxides and 2 hydrogens give me what? 2 water molecules. Okay? Now, you can do this when you still have half reactions, or you can just go all the way to the end and fix it then. The one thing that does end up happening is sometimes you'll end up with water on both sides of the chemical equation. And so then you just need to take the extras out. So we'll do an example for this one. Let me check. Okay, I've got 2 of them again. Let's just do one. Iodide and permanganate, or hypochlorite and that chromium complex ion. I think we should do the iodide one. It's kind of perverse, because that's the one you guys had so much trouble with. Okay, so half reactions, right? So we're going to have iodide on one side and iodine on the other side. And then I've got permanganate ion and manganese oxide, manganese 2 oxide. And then, let's see, I'm in O2. So Balancing for mass, what do I need up here? I need a 2 in front of the iodide. And down here, well, that's kind of a sad-looking oxygen. The manganese are fine. The oxygens are messed up, right? This side has 2 oxygens, that side has 4. So what do I need over here? I need 2 water molecules. And then to fix the hydrogen, I need 2 hydrogen ions? 4. 4 hydrogen ions over here. And then I've got all my elements balanced. Thank you. I'd like to say I was just checking to see if you're paying attention. Okay, thanks for catching that. So, balancing charge, right, we've got 2 negative charges here and none over there. So, add 2 electrons. And then this one, everything's neutral on the right side. Here I have a -1 and +4. So that's a total of +3, right? So that's going to give me 3 electrons that I need over here. Now what do we do? Yeah, we need to get the number of electrons the same. So I'm going to multiply the top by 3 and the bottom by 2. And I write that out there because otherwise I get confused and I screw up in the middle. So, oh, that doesn't show very well, does it? There's a ×3 and a times, there you can see it a little better. So I'm going to take all the coefficients and multiply these by 3. So this gives me 6 and 3 and 6. I'm just getting the least common multiple. 2 times 3 would be 6 electrons here. 4 times 2 is 8. 2, 2, and 4. Everybody okay with that? I'm going to show you the fix it at the end method. So first we're just going to balance this in acidic solution, and then we'll fix it. So we got our electrons equal, so now we'll add these together, and the electrons cancel out. And sometimes these get a little bit long, so we have to write small. So 6 iodide plus 8 hydrogen ions plus 2 permanganate ions is going to form 3I2 plus 2MnO2 plus 4H2O. You know that's a liquid, right? So it would be a good idea to check this before we go on. So here we have 6 I's and 6 I's, and 8 H's and 8 H's, 8 oxygens, and 2 times 2 plus 4, 8 oxygens. And the charges, everything's neutral over here, and we've got -6 and +8, so that's +2, and then -2 is 0. So that's balanced. That would be in acidic solution. But this says basic solution. So here where we have these hydrogen ions, that was the wrong pen. Did not want to do that. Here where we have those hydrogen ions, we need to add the same number of hydroxide ions. And we're going to add to this to both sides. So I'm going to add 8 hydroxide ions over here and 8 hydroxide ions over there. So what do these become? 8 water molecules, right? So let's make them that. So 8 H2O. Do we have water on both sides? We do. We've got 4 waters over here, and we've got 8 over there. And so if we subtract 4 from both sides, we can ditch this guy, and this will be 4. And then it's kind of a mess, so we really should, write it out more neatly. I was doing so well there. Oh, I thought maybe I could hit it, but no, not quite. Any questions?
So if we get H plus on the reactant side, we should think O is probably basic and then put on the solutions.
So the thing is, you're not going to know just from looking at the equations given. It's going to have to tell you if it's acidic or basic. And the hydrogen ions could end up on the reactant side. They could end up on the product side. And so you just have to look at the instructions. If it doesn't tell you, then it's a badly asked question. But you could claim ignorance and say, well, it didn't tell me, so I just did it in acidic solution. That's easier, right? So, any other questions?